Let's start by introducing who is teaching this class. So here is the course staff. There are two professors. One of them is Anka Dragan.
Hi.
Want to say something about yourself?
Yeah, I'm Anka Dragan. I'm new faculty here in ECS. I specialize in robotics. There we go. Anka Dragan, new faculty in ECS. I do research in robotics mainly and human-robot interaction. I come from Carnegie Mellon. I also took Intro to AI in my undergrad at Carnegie Mellon, and it was awesome, and it's kind of what got me into this field. So I am very excited to share this field with you this year.
Thank you, Anka. I am Pieter Abbeel, the other instructor. Let's also introduce the GSI team. So if the GSIs could stand up. I think most of them are on this side over here. We have Tianhao Zhang, Alex Lee, Abhishek Gupta. If your name is called and you're here, wave wildly so they know who you are. Abhishek Gupta, not able to make it in. Chris Lin, Colleen Devon, Davis Foot, Gregory Khan, Jacob Andreas, Karthik Narayan, and Wei Cheng Kuo, who I think is still on a flight back to Berkeley. All right, so let's move on to course information. You should have gotten an email from us late last night. If you are enrolled or if you are on the wait list, you should have gotten that email. If you didn't and you think you are enrolled, you think you're on the wait list, check again and also check your spam and so forth. This is the last time we will email you though. Going forward, all the announcements will be on the course webpage, which is on EDX and on Piazza. So make sure you sign up for both EDX and Piazza. Slight subtlety, don't sign up for EDX, but sign up for edge.edx. That's where the course lives. If you want to reach us, best way to reach us is Piazza. A lot of other students can help answer your questions. We will monitor that very closely. You can also ask private questions there, but by default, it makes sense to ask them publicly because a lot of people have the same questions. If there's something that you think doesn't make sense to ask on Piazza, feel free to email the staff list. If you think even that doesn't make sense, feel free to email us individually. This course will be webcast. We're trying to have some redundancy here. We believe Campus is recording this, and we're also Camtasia recording this. So hopefully that means it will be recorded every time at least once. There are also videos from the past. There are full 2012 edited videos, and there are Spring 2015 edited videos. What that means is, at that time, one of the GSIs went in and took out all the kind of redundant stuff in lecture and made every 1 hour, 20-minute lecture into something like a 1 hour and 2-minute lecture, and cut out the stuff that wasn't really directly kind of on topic maybe, or where maybe a student was asking a question, professor had to repeat it, cut out the student part because you can't hear it anyway in the video, things like that. So that's another place you could watch the videos even ahead of time. You want to already start learning everything now, you can tonight watch all those edited videos. The course technology is still a little bit new. edX, we've been using it for a little while, but it still has its quirks. We think it has a lot of benefits, but carry with us. If you see something quirky, let us know and we'll try to make it good. Through edX, we'll host your homework. So this will be auto-graded homework. There will be questions, you answer them in EDX. It'll directly tell you whether you got it right or wrong. If you got it wrong, you can try again. You can keep trying until you get it right. So the idea here is that we want you to keep learning, keep trying until you really understand what the answer is. And at that point, you'll know you have it right, you move on to the next thing. Same for projects. All the projects will have auto-graders, and we want you to be able to keep working till you get it right. And so you'll have a local auto-grader, so when you solve your project, you can locally run the auto-grader. Once you get full score on that, you upload your solution, and on edX, the same auto-grader will run on our side and should match, its response should be matched with whatever you saw locally. And so you know when you get it right, when you get it wrong, how many points you're still losing, and so forth. But we hope you keep working till you get everything right. Prerequisites, 61A, 61B, and 70. There actually will be a lot of math, but not in the first half of the course. So be prepared for that to kind of kick in only in the second half. Be aware of that. There is a self-diagnostic on the course homepage that allows you to check your math background. And check that if you're a little bit worried, because otherwise, week 8, you're going to be caught by surprise and see all of a sudden that there's a lot of math in this course. There'll also be a lot of programming. There'll be 6 programming projects. You can do those alone or in a group of 2. You have to only submit, like you can code together in your group of 2 and have one piece of code that is your solution. You get a budget of late days, 5 late days for the semester, meaning that you can choose when to use them. You can use at most 2 on any given project. So projects will always be due Fridays at 5 p.m. And then if you're between Friday 5 p.m. and Saturday 5 p.m. you submit, that's 1 late day you use. If you submit between Saturday 5 p.m. and Sunday 5 p.m., that's 2 late days. After that, it closes. That's for projects. Homeworks have no late days. You need to be on time. There will be 1 midterm, 1 final. It'll be on a fixed scale that's advertised on the webpage, so you know based on the points you're getting where you're going to land with your letter grade. We don't directly grade on participation, but if you end up falling right on the boundary, it might help if you answered amazing things on Piazza or something like that. Keep in mind that the exams will be the hardest part, though. So keep that in mind as you work through the course. It's a very different environment to solve a problem when you know you can keep trying until you get it right versus solving a problem when you have 3 hours, you're time constrained, and you don't know whether you have it right or not. You're only going to find out a few days later. So don't think just because you're cruising on the homework and the projects that you are necessarily also prepared for exams. Everything is set up for you to talk with us, talk with other students, and so forth. What we ask from you is that you acknowledge any collaborators you had, only work with one other person for your project. For homework, you can talk with other people, but you need to submit your own work. You can't just submit somebody else's work. Okay? We want you to talk to each other, but if you submit other people's work as your own, we will try to detect that very hard and come down on you for that. There will be contests. A couple of projects will have an extra credit part at the end of the project where you can compete against other students with your AI agents. See which AI agent works best. Exam dates. We're waiting for confirmation of our exam room for the midterm. It will be the week right before spring break. Make sure you're here. We will not have a makeup midterm, so we'll hopefully be able to announce soon exactly which evening that is going to be. But make sure, for now, you have it marked off all those evenings. The final exam will be Thursday, the 12th, in the morning. We didn't choose that early time. We would never pick that. That's chosen by campus. Again, there will be no makeup. So if that's a time you cannot make, this might just not be the semester for you to take 188. Laptops. It turns out that if the student in front of you has their laptop open, it can be distractive for the people behind that student because they're like, oh, what are they buying on Amazon, or what are they telling their friends, and so forth. So we ask that if you want to look at your laptop during lecture, that, okay, today you can't really move around, but on days where you have a choice, that if you use your laptop, you kind of seat more towards the back, so people behind you have a choice to actually be sitting in front of you and not be distracted by the bright spot that's right in front of them. Textbook-wise, there's no required textbook. The intent is that all the material you need to know is in the slides, homework, discussion section handouts, projects, past exams, and so forth. But if you want to learn more, the textbook that we recommend is the Russell and Norvig book, 3rd edition. 2nd edition is actually fine too. 1st edition is quite different, so we wouldn't want you to look at the 1st edition. Discussion sections. These are optional. We hope they're good and that you're excited to come, but you're not required to come to these discussion sections. They are a review of materials covered in class, a quick review at the beginning, followed by you solving some problems on those materials. And the GSIs will help you kind of work through those problems and then show how they work through them. You are welcome to attend any section of your preference. What we will do is we will post a poll on Piazza where you can indicate your intent of which section you are going to attend. Then you can look at that poll and you can decide, do you want to go to the 2 to 3 p.m. section that has 500 people in it and there's only 30 seats, or do you want to change your mind and go to a different section? And our experience is that the first week this will be a disaster, there will be way too many people, but over time this will sort itself out pretty quickly. We will also record discussion sections, meaning one of the GSIs will, on Monday evening or on Tuesday, kind of collect what happened in section, make sure that they have a good grasp on what worked, what didn't work, then make a video recording of them going through the materials that were covered in section. So you can also do section remotely. We'll be able to interact with the GSIs, we'll be able to look at the materials that were covered. No section this week, be too late anyway, because all sections are right now scheduled for Monday. There'll be another type of section. We call them exam practice sessions. What's the point of the exam practice sessions? As I said, it's very easy to think that you're fully up to speed on the materials because you're doing well on the homework, but maybe you had to try multiple times and you forgot about that. Maybe you had critical insights you got from a friend while you're solving the problems, and you kind of forgot that. You look at your grades like, oh, I have 100 out of 100 on my homework, I'm doing good. We want to make sure that you have a weekly reality check on where you're at. And so we have exam practice sessions, again optional, but the GSIs will bring 1 or 2 past exam questions on the topics that you just solved on problems on in your homework on those same topics, and you will be trying to solve those in that session. And you can also see how they would solve them, ask questions, and so forth. And these will be actual past exam questions. So if you try to work through those on your own, you're doing well, you know you're in good shape. These will start the week of the 8th. So next week, only regular discussion sections. The week after that, there will be 2 types. Exam session and regular discussion session. Next week, the time slots allocated to the exam practice sessions will be allocated to regular discussion sections, so there is more space for regular discussion section. That's just a one-time thing where all the slots we have next week will go to regular discussion section. Just a one-off thing. There will also be a webcast of the exam practice session, same as for discussion session. All right, what's important this week? Register for the class on edX, register for the class on Piazza, work on the P0, Project Zero Python tutorial. It's out, it's due on Friday at 5 p.m. You might ask, why 5 p.m., why not midnight? We specifically choose 5 p.m. because we want to give you a better shot at doing something else than 188 on your Friday evening. We hope we succeed. There are one-time project-specific office hours that will be on Thursday and Friday. We're still getting the room confirmed, but hopefully soon we can confirm when and where that'll be. It'll be Thursday and Friday. There used to be instructional account forms. That's not how it works anymore. How it works now is that rather than getting a form, you go online and request your account. You don't need this account for anything in 188. Not needed. We don't use your account at all. But a lot of you use those accounts to get printing quota and other things that are useful. So there's a link on Piazza that points you to where you get that account. The math self-diagnostic is up. Work on that. It's not scored. It's not for your grade. It's for you to make sure that you know whether you are prepared for the second half of the course mathematically. Mark the exam dates in your calendars, or for the midterm, mark the entire week for now. Sections start next week, if you are waitlisted, which is true for about 200 of you, maybe 280. And you want to find out more, talk to Michael David Sasson. He knows exactly what the chances are, whether things will grow, not grow, and so forth. Regular office hours will start next week. There will be a pinned post on Piazza that will have always the up-to-date office hour information. That's the latest. In the meantime, if you want to catch Anka or me, catch us right after lecture. All right. Any questions about logistics? Yes?
Maybe you can have the guy who's dealing with the weight just send out, I don't want us all like sending him an email, maybe you could just send a general informational thing on Piazza.
And a general informational thing on Piazza about?
About how the weight list works.
So the post on Piazza says essentially how it works, which is Michael David Sasson is in charge of the wait list, and contact him if you have any questions about how this will work out.
Yeah, I'm just expecting his inbox is going to get flooded.
Yeah, his inbox will probably get flooded. I know he's working on trying to expand the course. I don't know if he'll succeed or not. So I know he's trying. I just don't know if he'll be successful. And I don't know about how many exactly if he is successful. So he's definitely trying. You don't need to go tell him, please try to expand. He's on that, but I don't know the success chances. Other questions about logistics? All right, let's get started then. So today we'll look at what is artificial intelligence, what can AI do, and what is this course? And maybe let's start with something that might be some of your sources for AI, which is science fiction movies. So who do we have here? Characters from Star Wars, right? The gold-looking one, C-3PO. What does C-3PO do? Essentially machine translation, right? Google Translate, but in a physical incarnation. So we have a protocol droid here. Back when this movie was originally made, people thought maybe those translators would come incarnated in a body. These days it's just in a computer. But that's one of the early ones where we see something like that. Since then, things have started to change. C-3PO and R2-D2 were pretty helpful. Terminator kind of came back from the future to, well, not be so nice to us. Then a little later with the Matrix, people started to get worried not just about robots, but also how software could affect us. Robots could start looking like people, which could make it really confusing. Or it could even be the case that they couldn't exactly look like people, but we could still fall for them and let them have our way with us. So overall, sci-fi might sketch a pretty grim picture at this point in terms of worrying about AI. If you look in the news, this is an article from about a year ago. This is Elon Musk, a big tech entrepreneur, saying artificial intelligence is our biggest existential threat. Around the same time, a new study was launched to study the long-term effects of artificial intelligence. Elon put his money where his mouth is and put down $10 million towards that study effort and so forth. That was a year ago. Just a few weeks ago, that became $1 billion. So there's definitely a lot of interest in kind of exploring what AI might do for us. You could ask, well, before we start this class, are there some things maybe somebody could be worried about? Well, let's take a rudimentary look at hardware. Okay? Let's see what can we compute in a computer compared to what animals can do. If you have a fly, that's about 10 to the 5th, so 100K neurons, about 10 to the 7th synapses. Okay? AlexNet, one of the best known deep neural nets, has an order of magnitude more, 10 to the 6 and 10 to the 7. A mouse has even more than that. A human has even a lot more than that. But let's do a little calculation. Let's assume each synapse is a flop, and that it can fire or now fire once per second. Totally rudimentary, not precise, but at least to get a kind of gist of where we're at. Then the human brain can do about 10 to the 15 flops. Okay? So 1 petaflop. If we can set up a machine that computes at 1 petaflop, we got essentially the equivalent compute power of a human brain. Not saying we'd have the right software, but at least we'd have the right hardware, or maybe not the right hardware, but at least the hardware computational power. What would that take right now? That would take about 100,000 current CPUs. Wondering? 100,000 current CPUs? Can I put those in a garage or something? Well, if you have money, about $5,000 per hour on Amazon's EC2 to rent the equivalent of a human brain's compute power. So it's not completely impossible to get that compute power together. Now in this class, we're not going to focus a whole lot on philosophy, but I did want to bring it up in this first lecture. And I do want to give you a chance to kind of find out more on your own. And 2 books I'd recommend you look at if you're interested in what are the repercussions of AI, where is it going, that are pretty good reads, are The Second Machine Age, which essentially describes what maybe the slightly nearer term effects of AI are going to be. And kind of the storyline there is roughly, what are the big changes that have happened in human history? The first big one they call out is the agricultural revolution. We switched from gathering food to putting animals to work the fields for us, and now that opened up time and we had more power to kind of get the things we want. The next revolution was the Industrial Revolution. We now did not use animals anymore, we used machines to do a lot of the physical work for us. And so the second machine age here refers to now not just using machines for physical labor, but using machines for thinking labor. So it's a very interesting read. The other one, Superintelligence by Nick Bostrom, is essentially talking about how might we achieve AI, and then asking the question, well, if really we were to achieve AI, would we really just achieve AI? Or once you achieve AI in a machine, wouldn't that immediately transition into something that's much stronger than human intelligence? Because once you achieve human intelligence and you can copy and paste programs and so forth, you don't need to raise a toddler from scratch to kind of have a new human when you're working with a machine. Maybe things will amplify very quickly once you reach that human level of intelligence, and that amplified intelligence is called superintelligence. Another good read if you are excited about the fear about AI. Why take this class? My 2002 answer would have been largely because you want to learn about AI. Maybe even want to continue to learn even more about AI during a PhD, but not exactly the class is going to maximize your job opportunities. The 2016 answer has actually changed a little bit. I'm still hoping you're here because you want to learn about AI. But a lot of jobs have started to emerge that actually have at their core AI. Just to put some numbers up, this is from Bloomberg, kind of quantifying industrial activity. Newly funded AI startups by year. In 2010, that's 2. And by 2014, that is about 16. So there's a very fast growth there in terms of the number of startups being funded. The amount of funding going to those startups is also rapidly growing. It's just one indicator of the fact there's a lot more industrial activity than there used to be that builds on AI advances. A lot of these will actually not necessarily go for superintelligence or anything like that. Really what they're doing is kind of amplifying the innovation cycle. So what happens is you are innovative. You build a new product, something new. You have people use that. They like it. You collect the data from them using that. By default, you would analyze that data by hand and then recode your software, your algorithms to make them better. But with AI, that process gets sped up. Your AI analyzes the data with you, improves your algorithm. Now you're better than the competition, even more better than before. You keep getting more data from people using your system. You kind of perpetually stay ahead, so to say. Once you have that advantage of having had more data, leverage that and keep doing that. Some examples that you might have seen, Google searches like that. They had a better search algorithm than the others back in '98. People start using it. Wherever they clicked when they found things was not always the top link, but when they don't click the top link, Google finds out that something else is actually more relevant. You can use that to improve their algorithm. A lot of that is through artificial intelligence, automatically improving the search results that you get, and this then makes Google even better. You're again inclined to go to Google. This keeps going on and on. Tesla Autopilot, recently rolled out, pretty gutsy. I mean, that autopilot was not 100% reliable when it was rolled out. Was not advertised as 100% reliable. Say you need to still be at the steering wheel, be careful. But the bottom line is that within the first week, there were a lot of improvements. Why? People were trying it out. It was doing the wrong thing. People would grab your steering wheel, correct it, and then that data would go back to improve the autopilot. and this way, this kind of cycle kind of perpetuates itself. Another one that will probably happen in the near future, Facebook M, you might have heard of that. It's a personal assistant built into Facebook Messenger. Initially, it's people who kind of jump in when you have a question. You're like chatting away and like, oh my God, we should go to a restaurant tonight. And then somebody jumps in and like, oh, I see you are near, I don't know, some ramen place. You should check this out. And you might say, oh yeah, I want to check that out. And then they're like, okay, that was a good suggestion. The system logs all of that. And over time, the system starts helping. The system now might, instead of just the humans working in the back, the system might have maybe a guess of 5 or 10 things that you would like suggested. It will show those 5 or 10 things to the human in the back. That human will maybe narrow it down to 1 or 2, suggest those to you, see what happens, and the system will keep improving. So this cycle of improving thanks to data collection, I think will be very big in the next 5 to 10 years. All right, but I really hope you're here mostly because you're excited to learn about AI. What is AI? Well, some kind of science, making machines. One way to define it is science of making machines that think like people. This is initially how a lot of people thought about AI. So what you want here is a system that essentially mimics the thought process that we have going on in our brains. What is that called now? It's called cognitive science, right? That's the field that dedicates itself to this way of studying AI. Now, just thinking like people might not actually get you what you want, so then people started to transition to asking the question, can we build a system that acts like people? Okay? So now you don't worry about the thought process leading up to the actions, you just wanted to do the right thing, so to say, like people would do. What's a good example of this line of work? Anybody heard of the Turing test? All right. Turing test is all about, so in the Turing test, you are sitting, so to say in the modern day Turing test, you're sitting behind your computer. There's somebody else sitting behind another computer. You're chatting with them. But it could be that the other person is actually not a person, it's a computer. And the question is, can you distinguish between whether that other side is a computer, that well a person? It has a lot of upside to think about things that way, also some downsides. When you want to make a system look like a person, you're going to impoverish its capabilities. Like, even if a computer could answer right away, what's the square root of 1,435 or something, if it needs to look like a person, it's going to take some time, make some errors to kind of look right. And so a lot of the research around the Turing test then ends up evolving around kind of how do people do kind of not so good things and making sure you mimic those. And that can be a little bit of a distraction if you want to build a useful system. Another way to define AI would be to say, well, we want systems that think rationally. That's essentially the mathematical, philosophical way of approaching things. We want systems that have, let's say, a set of actions, and whatever follows from those actions, it's allowed to conclude and so forth. That's, I would say, still a work in progress to see where that'll lead us. And the definition we'll be using in this class is that we want to build systems that act rationally. What does that mean? What are rational decisions? So rational will be defined in a very precise way in this class. So it might not have the meaning that you already have in your mind for the word rational. What it means is maximally achieving some predefined goals. It's not concerned with the thought process leading to whatever happens. It's only concerned with whether those goals are achieved and to which extent. The goals will be expressed in terms of utility of outcomes. So for every possible situation the system finds itself in, there will be a number associated with that that scores how good that situation is. And an AI system, the types that we're considering, tries to maximize the expected amount that that number takes on. Expected because a lot of systems are not deterministic, so you can assume that there will be a specific number coming out, there will be a distribution over possible outcomes. And so being rational means maximizing your expected utility. And so a more precise title for this course, rather than artificial intelligence, would be, this course is a course on computational rationality. Okay? So all we're going to be doing for the remainder of the semester is try to design systems that maximize expected utility. So somehow there'll be some kind of function, utility, try to optimize its expected value. Now, first thing you might ask yourself is, well, if we want to build those systems, how are we going to start? We kind of have some kind of proof of concept, which is natural intelligence. Can we get inspired by that? So why don't we look at the brain, see what we can take from there. So human minds are very good. In fact, they're better than computer systems at pretty much anything that AI is trying to achieve, at least at this point. But it's very hard to reverse engineer the brain. That's the field of neuroscience. Trying to figure out how the brain works is still a big, open-ended problem. Some little bits are known and have inspired some work in AI, and that's not a bad thing, but to kind of hope that you can just replicate how the brain works is just not something you can start on because we don't know yet how the brain works. One way to think of it at this point is that brains are to intelligence as wings are to flight. What do I mean with that analogy? Initially, when people were working on flight, they weren't really getting things to fly. The reason they weren't getting things to fly is they were looking at biology and they were trying to copy it very literally. They were trying to build flapping wing systems. And it turns out only once people started focusing on the essence of flight, namely that wings will generate lift, did they start having the breakthroughs that led to planes and so forth. And so same thing here for our AI efforts. We might look at the brain and say, well, these things can inspire us. The way the brain is able to process this but not that might tell us something about how feasible it is to solve a certain problem and so forth. But we don't want to just directly try to mimic it. It's even harder than in flight because we don't even know how the brain works. The key lessons we'll use at a high level are that the brain uses memory, things you remember from the past, and that you can rely on to do smart things now, and simulation, which means the brain can think ahead. If I were to do a sequence of things, what would the consequences be? And would that be a smart thing to do, or would that lead to bad outcomes and I shouldn't do this? All right, before we dive in on how we're going to approach this, let's take a look at the history of AI. Let's start with a video, actually, to give you a feel for what things were like in the early days. See if I can find a microphone. Plug in. Come on. Enter? It might not open the right player. Let's see. Here we are.
The Thinking Machine.
Hello again. With me tonight is Professor Jerome B. Wiesner, Director of the Research Laboratory of Electronics at MIT. Dr. Wiesner, what really worries me today is what's going to happen to us if the machines can think. And what interests me specifically is, can they?
Well, that's a very hard question to answer. If you'd asked me that question just a few years ago, I'd have said it was very far-fetched. And today, I just have to admit I don't really know. I suspect if you come back in 4 or 5 years, I'll say, sure, they really do think.
This is in
Well,
the
if you're
50s.
confused, Doctor, how do you think I feel?
We're just really beginning to understand the capabilities of the computers.
I've got some film to illustrate this point, which I think will amaze you.
That man isn't playing checkers against a computer, is he?
Sure, and it plays pretty well.
Now, which color...
While most computer scientists saw it as a mere number cruncher, a small group thought that the digital computer had a much grander destiny. Being a general-purpose machine, it could be programmed to do things which in humans require intelligence. Play games like checkers and chess, and solve brain teasers.
Let's see what it's turning out.
The field became known as artificial intelligence.
Can machines really think? Even the scientists argue that one.
I'm convinced that machines can and will think. I don't mean that machines will behave like men. I don't think for a very long time we're going to have a difficult problem distinguishing a man from a robot. And I don't think my daughter will ever marry a computer. But I think the computers will be doing the things that men do when we say they're thinking. I'm convinced that machines can and will think in our lifetime.
I confidently expect that within a matter of 10 or 15 years, something will emerge from the laboratories which is not too far from the robot of science fiction fame.
They hadn't reckoned with ambiguity when they set out to use computers to translate languages.
A $500,000 supercalculator, most versatile electronic brain known, translates Russian into English. Instead of mathematical wizardry, a sentence in Russian is to be fed in...
One of the first non-numerical applications of computers, it was hyped as the solution to the Cold War obsession of keeping tabs on what the Russians were doing. Claims were made that the computer would replace most human translators.
At present, of course, you're just in the experimental stage. When you go in for full-scale production, what will the capacity be?
We should be able to do about, with a modern commercial computer, about 1 to 2 million words an hour. And this will be quite an adequate speed to cope with the whole output of the Soviet Union in just a few hours computer time a week.
When do you hope to be able to achieve this speed?
If our experiments go well, then perhaps within 5 years or so.
And finally, Mr. McDaniel, does this mean the end of human translators?
So yes for translators of scientific and technical material, but as regards poetry and novels, no, I don't think we'll ever replace the translators of that type of material.
Mr. McDaniel, thank you very much.
All right, so that's what people were thinking back in the 50s and the 60s, which is when they had just started to build computers effectively. And they right away, what happened is, in the early days, they built a circuit model of the brain, very small circuit model of the brain, but they built something that's a little bit like a brain. Turing described how computers can just do number crunching, but can also compute more complicated things. And so there was this kind of feeling that these machines are going to be able to think, and maybe even very soon, because of all these early successes. Successes amplified in the 60s. There was an early AI program that could play checkers. We saw that there. There was a logic theorist, which could do logical reasoning, which is hard for people to do. There was an engine that could prove geometric theorems, which again is hard for people to do. And then in 1956, the word AI was coined at a meeting in Dartmouth, where people said, okay, let's call this new field artificial intelligence. Not too much thereafter, it was a complete algorithm for logical reasoning. So there was a lot of progress, and you had kind of the spirit of, this is going to go quick, we're almost there. We're 50 years later now, of course, and we're not there yet. But these were some very smart people at the time giving their opinions on where things were headed. People start realizing that to really build an AI system, it needs to know about a lot of things. And to know about a lot of things, what they started doing is encoding a lot of information about the world into knowledge bases. And so you would have efforts where people like think about every fact that it might be true about the world and so forth, put that into a logical format, squish it into those knowledge bases. These were the expert systems of the time. But they kind of flopped. They didn't give the results people were hoping for, despite a very big investment in those systems. And so at that point what set in was a AI winter. What's meant with that is a time where people were less excited about working on AI, and especially government agencies were not very excited about sending money to researchers who wanted to work on AI, which of course kind of hinders progress. In the 90s, what we saw happen is a resurgence of activity in AI, and largely what started happening is that people started working with probabilistic approaches. So it turns out if you try to encode things about the world and you try to do everything deterministically, it's really hard to do that right. You say like, oh, birds can fly, but then is a penguin a bird? Yes, but a penguin can't fly. So birds can fly, but not if they're penguins, and so forth. And then maybe there's like one type of penguin ultimately that can fly. You kind of keep busy for a long time making exceptions to exceptions to exceptions and so forth. And so by using probabilistic reasoning, you get around those subtleties by now assigning probabilities to things rather than ground truth values. Another part of it is that for probabilistic reasoning, we needed advances, theoretical advances that people figured out at that time. You need more compute power. Back in the 50s, the compute power of the machines they were working with was less than the current compute power of your phone. Maybe less than the current compute power of your fridge or your microwave. And yet they were thinking that that was going to give them AI. And that was a little optimistic. So where are we at now? Since the 2000s, and then onwards. Actually, let's take a break here, and then after the break, let's start looking at what AI can do now. All right, let's restart. And let's take a look at what AI can do. And so let's do this together. And let's ask some questions. So first question. Can AI play a decent game of table tennis? What do you think? Hear a lot of yeses. The answer is true. There are some robots that have played some pretty good table tennis. Can it play a decent game of Jeopardy? Yeah, happened not too long ago. Actually beat some superstar human at it. Can it drive safely along a curving mountain road? It's actually happened. It can do that now. Can it drive safely along Telegraph Avenue? Can anyone drive safely along Telegraph Avenue? Not so sure. Can it buy a week's worth of groceries on the web? Yeah, that's easy for AI. Can it buy a week's worth of groceries at Berkeley Bowl? Elbowing some people around, making sure it doesn't drop the objects it's picking up? Not really, that's still too hard. The physical interaction there and the interaction with the people that are also shopping there is well beyond what AI could handle at this point. Can it discover and prove a new mathematical theorem? Here's some yeses, here's some nos. It's kind of a yes and no at the same time. What do I mean with that? Can it prove a theorem that nobody's been able to prove before the AI took charge in it and then proved it? Yes, that's happened. And we'll see an example later. But can it actually discover a theorem? That's much harder. Imagine how many theorems it could come up with. You give it the axioms of calculus, and now it's like, okay, 2 + 2 is 4. I've just proved it. Let's prove 2 + 3 is 5, and so forth. So any kind of idiotic thing that we would never care about that might be provable, it might then go ahead and prove. And so there's a lot of things you could prove, but having a taste for what theorems would actually be helpful, would be insightful, is really hard. Converse successfully with another person for an hour. Define successful. Good question. So this is a little bit debatable in some sense. I would say not successful at the level a person could do this, but maybe for some people, they might talk with an AI for an hour and be quite happy. Perform a surgical operation. Who here would be happy to get their kidney removed and donate it to somebody who needs it, let's say, by a robot without human intervention? 1, 2, 3, 4. Wow. That's 4 or 5 more than I would have thought. I'll keep you in mind for our surgical robotics research. Well, there's a subtlety here in terms of what you mean with a robotic surgeon, right? Right now, it turns out a lot of surgeries happen by a robot. The Da Vinci system by Intuitive Surgical does about 500,000 surgeries per year. It's not exactly removing a kidney, it's a gallbladder removal typically. But the way it happens is in pure teleop. There is a surgeon sitting at a station holding essentially 2 robot end effectors, moving those around, and whatever motions they make here with the robots they're holding are then mimicked by a smaller robot inside the patient. That smaller robot also has a camera. The surgeon can see the camera feed. And so it's really the surgeon doing all the work there. There are some other ones where computers do some of the work. LASIK surgery, some of it is done, because it can be done more precisely by computers taking charge of some things, but the humans still tend to make the decisions in terms of what should happen for which patient. Put away the dishes and fold laundry. Kind of mixed here. How about we say yes, because we did some of that in my lab, but the truth is that it's still a long way to go to do this reliably, but I'll show you a video later that does some of it. Translate spoken Chinese into spoken English in real time. This can be done. It might not be the best translation, it might not be the best English, but if you don't speak Chinese, it's going to be a lot better than just listening to the Chinese. Write an intentionally funny story. Maybe it depends on what you mean with intentional, but like really intentional, that's still beyond the grasp of what systems can do. Let's look at some examples here of what I mean with an unintentionally funny story. So, back in the 80s, there was a lot of work on trying to build systems that can write stories. The idea being, if you can write a good story, that system must have understood something about the world, what the world is like. And so it's a good way to kind of make it more concrete whether you are making progress on building an AI system or not. So let's look at some stories from the Tailspin system. Okay, first one. One day, Joe Bear was hungry. He asked his friend Irving Bird where some honey was. Irving told him there was a beehive in the oak tree. Joe walked to the oak tree. He ate the beehive. The end. So something like this just happened. So what happened here? What's happening with this language generation system? Everything being said here, kind of these sentences and the story kind of, we understand what's happening in that story. It's only wrong in a tiny little way. What's the mistake it's making? It's actually doing well. It understands when somebody's hungry, finding food is good, honey is a kind of food, being told where that food is good, so you go there. And then the one thing it's slipping up on is that if you want to eat the food that's in a container, you got to open up the container first and get what's inside. But that's the one mistake it's making, and because it makes such a tiny little mistake, it's funny to us. Here's another one. Henry Squirrel was thirsty. He walked over to the riverbank where his good friend Bill Bird was sitting. Henry slipped and fell in the river. Gravity drowned. The end. So this story is actually completely correct. It's just at the very end. It's telling it in a very different way than we would tell it. When we talk about drowning, we wouldn't talk about the fact that gravity pulls people under the water. We would talk about the fact that there is somebody who's drowning, and that would be what we talk about in that sentence, not the gravity force. But it's very close. Here's another one. Once upon a time, there was a dishonest fox and a vain crow. One day the crow was sitting in his tree, holding a piece of cheese in his mouth. He noticed that he was holding a piece of cheese. He became hungry and swallowed the cheese. The fox walked over to the crow. The end. So this one is even more correct. I mean, we know about dishonest foxes and vain crows. Crows can be sitting in trees, they can be holding a piece of cheese in their mouths, and so forth. But why are we saying the fox is dishonest? We're never following up on that. Why are we saying the crow is vain? There's never any follow-up on that. There's just a lot of things that we just wouldn't say those things if there's no follow-up or if there were follow-up in the way that we have over here. But technically, it's actually very close to correct story. Where are we now? This is 1984, unintentionally funny stories. Well, maybe we can ask Siri. Siri, tell me a story. What does Siri say? Well, if anything, us AI researchers have learned our lessons and have learned that we're not that good yet. And so, once upon a time, no, it's too silly. So, it is essentially just saying, I don't know how to do this, but telling it is in a nicer way than just saying I give up. What are other language technologies? One thing in language that matters a lot is speech recognition. So let's take a look at an example of speech recognition in action. So here's a video. Of
friends, family, and classmates said their final goodbyes yesterday at her funeral in East Falls. Now, Asia Adams was buried today, and on this day, a major break in the case. Police sources tell NBC 10 that a person is in custody and appears to be a strong suspect. They will have more information in the morning. Reporting live from police headquarters, I'm Denise Nakano, NBC 10 News.
Good evening, and also new at 11 tonight, a Pennsylvania state trooper
injured. So what do we see here? Actually, pretty good transcription. And if you were to reread what was transcribed aloud, it would actually match quite closely with what was being said. There were some subtle mistakes, like goodbyes was spelled as in I'm going to goodbye, Best Buy kind of stuff, rather than saying goodbye, but it's pronounced essentially the same way. And so this is actually getting pretty close. Still, I mean, a lot of progress to be made in more cluttery environments where there's other speech in the background, there's noise and so forth. But in these cleaner environments, things are starting to work quite well. You can do the reverse, text to speech. You get that in your GPS when you get instructions about where to make a turn and so forth. Dialogue systems, that's of course a harder problem, but things are starting to come in place. You might not always enjoy them. You call somewhere, there's a dialogue system picking up the phone, trying to route you to wherever you need to be in that phone call. Language processing technologies. Good example, question answering. Talked about Watson, that's essentially question answering. I know Watson asked the question, but really it's trying to give an answer to some kind of description just in the form of a question. It's now being used for things related to medical decision making. Machine translation. That's the problem that was referenced to in that 1960s video. That was what drove a lot of the research at the time. Why? Some really smart Russians who were not our buddies at the time, if you were in the US, were doing some really cool work over in Russia. The US wanted to keep tabs on what they're up to. And so you needed to translate everything they're doing there into English to make sure you know what they're up to. And so people wanted automatic translation systems from Russian to English to be able to keep up with what's happening there. These days, of course, other applications, not just for translating Russian. It's actually pretty good. It's not what an expert translator would give you, but it gives you the gist of what's in the article. Web search, another very important language processing technology. Text classification, spam filtering. I mean, actually, a lot of you might not even know what spam is, but when I was a student, we used to get these emails that would be all kinds of advertisements for things I can't even talk about in lecture, and they would come right into your inbox, because spam filtering wasn't good enough. The automated system would not realize that those things had to be kept out because this is not what I want to read. These days, spam filters have become so good that you rarely see anything in your inbox that you didn't want to see. But that's all using AI systems, trained on a lot of examples, a lot of data of people in the past marking things as spam. Let's think about another AI domain. And one way to think of it is, why are we looking at AI domains? Like, we looked at language, that's one domain. We're now looking at vision, we'll look at robotics. Often a way to make progress on AI is to pick a specific domain where your problem can be more concrete. Rather than saying, I want to build an AI system, you say, can I build a system that can understand what it's looking at? That doesn't mean by doing that you're going to build a full AI system, but you might be solving part of the puzzle that might also inspire you to later build a bigger part of the puzzle, and you can start measuring more concretely whether you're making progress rather than just having some arbitrary metric, how AI is this thing that I just built. So one example people look at a lot, object and face recognition. If you use any kind of social networks, Facebook, Snapchat, and so forth, they have systems that can recognize who is in your images. Of course, part of it is that they know who your friends are, they know how to narrow it down to most likely people you already know, but still, you might have more than just a handful of friends, and it usually knows who is in the picture. That's an AI system in the back figuring out who is in that picture. Scene segmentation, how do you figure out what a scene consists of? For a computer, if it gets a picture looking this way, it's just a bunch of numbers. There's nothing in that picture that says student, 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 and so forth. No, just red, green, blue values on a grid. And somehow it needs to make sense of that. For us, that's very natural. billions of years of evolution and so forth have given us a system that can understand what we're looking at, but the computer starts from scratch. Still, recently there's been a lot of progress in being able to understand better what those pixels are. Image classification, understanding what's in an image, horse versus cat versus dog, and so forth. Let's take a look at some demos here. First one will be from a popular movie made by our former California governor. Let's see. All right, we'll leave you to watch the rest of this movie at home. This is Terminator 2. What do you see here? That was a vision system in action. That system was identifying what it's looking at, understanding what is what in its scenery. Can we build something like this these days? Well, let's take a look. Here is a actual, so that was just a movie. You can do whatever you want in the movies pretty much, but now we'll look at an actual AI system. What's going on here? Frog, fox, Dalmatian, bulldog, frog, terminate frog. Effectively, that part we got under control right now. So these systems are starting to come in place. They're not perfect. It's still an AI research domain. There's a lot of progress in that direction. Robotics. What are some problems there? Robotics consists of mechanical engineering and AI, largely, the way we look at it. We're not going to look at the mechanical engineering parts here, but a lot of the challenges are in the AI. How do you get that system to be smart enough to do the things you want it to do? So let's look at some examples. First one here, one that you might have seen on the streets. This is the Google autonomous car as of a couple years ago. This is from the dashboard cam. This is all autonomous, detecting pedestrians, stopping for them, navigating a toll plaza, navigating something that might be a little scary, detecting deer. Another difficult merge, and so forth. So this is the kind of thing that starts becoming within the realm of what's possible here. This requires understanding what you're looking at, taking the right action based on what you're seeing. Here's another one. This one is from my group here at Berkeley. Slightly sped up video, 200 times. But what you see here is actually a robot that lives at Berkeley, lives in Satarja Dye Hall, knows how to fold towels. We could fill 2 lectures watching this in real time. Here's another one. Whoa. Robot soccer. This is a competition where you program the AI for the Sony Idol robots. sometimes what will happen if you allow your AI to learn, it might do things that you might not anticipate. Here's an example of that. It's supposed to get to that ball and kick it. Now, that's what you'd hope something like reinforcement learning will give you, something Anka will cover for us about 10 lectures from now. So here's another example. Petman, since renamed Atlas from Boston Dynamics. See what Atlas can do. It's hard to not think that this looks kind of a little bit like a Terminator. Nice little pose there. When it has time to spare, does some push-ups. That reminds me, actually, if you ever want to try to run into me while I have some time to spare, which is not going to happen that often, there's something called TAC, Total Athletic Conditioning, organized by the Berkeley Gym, Monday, Wednesday, Friday, 5:30 till 6:30. Serious training on the track, highly recommended. It's good to be in shape, and being physically strong can also help you mentally. So it's one thing I highly recommend aside from studying really hard for AI. All right, so those are some examples of where we're getting to. That's robotics. We'll see more of that, and we'll see a lot of the algorithms underneath this. What enables these kind of things? Other areas in AI, logic. What you see on the right there is essentially the first theorem that people were trying to prove. So it was a conjecture at the time, and then a computer was able to prove it, actually with a relatively short number of steps, and people were not able to do this. Other logical things, fault diagnosis. If something fails, what are the things that could have caused this? A lot of this is now done probabilistically, but some of it is still done with logic. Deduction systems, constraint satisfaction problems. For example, you want to solve which class is going to be in which room at which time. That's a constraint satisfaction problem to satisfy constraints of that not the same room can be used by two classes at the same time. Maybe some classes shouldn't be scheduled at the same time because usually students take both of those classes and so forth. We'll see that in a couple of weeks from now, how to solve those kind of problems. Another one that's been very inspiring for AI is game playing. Maybe the most memorable one here is chess. In May '97 was a big match between Deep Blue, built by IBM, and Kasparov, the #1 human in the world at the time for chess. This is the first match won against the world champion. Now, they played multiple matches, and overall, Kasparov still won. But he said, I saw some intelligent, creative play there. What was it doing underneath? It was considering 200 million board positions per second. Inside that fridge-like looking thing is a supercomputer from that time. Humans understood, or said they understood, 99.9% of the moves. Said, yes, this is the move, it makes sense because of that reason. So it was really kind of uncanny what was happening there. Now you can do the same thing with a normal PC cluster, or maybe in just a PC, but 97, this took a supercomputer essentially. It was open. So an open question though at the time is, how does the human cognition deal with this? Humans don't consider 200 million board positions per second. Yet, the best humans were making very similar decisions. So even though the computer was getting on par with humans performance-wise, in terms of thought process underneath, it was still very different, and maybe there's still a lot of progress to be made to think more efficiently than what was done there. 96, there was a rematch. 96 was the first match. I could feel, I could smell a new kind of intelligence across the table, is what Garry Kasparov said at the time. It's like you could put a little smell scenty thing in your car and smell that new kind of intelligence. 97, Kasparov lost and said, Deep Blue hasn't proven anything. That statement might prove more about humanity than about AI. Recently, a lot of advances in Go, which has largely been considered an even more difficult problem for AI to solve. So there's a lot of work being done there. There's a lot of AI progress in decision making. Problems like scheduling, airlines, military, route planning, Google Maps. How does it know how to route you? Medical diagnosis. What might be causing the symptoms you have? Search engines, spam classifiers, automated help desk that route your question to the right person, fraud detection, credit card fraud. You might sometimes get a call or a text message saying, can you confirm this purchase, that it was really you? That's because some automated system has seen that this is something that normally wouldn't happen according to its findings, and it wants to make sure your credit card wasn't stolen. Credit card companies need this because they cover fraudulent transactions, and so they need to detect them as quickly as possible to prevent them as much as possible. There's a lot more things that happen with AI systems. So what we want to do is designing rational agents. An agent is some entity that perceives and acts. So it could be maybe a little robot that enjoys having apples and that somehow is going to try to get the apple. The way we formalize this is that there is this agent, which is something that can compute things. It has sensors. The sensors get to perceive what the world is like. This could be a digital world, this could be the real world, but it's somehow getting input from what the world is like. Then does some calculation. The agent computes and then decides what to do with its actuators. This could be physical actuation. This could just be an action inside a computer. The way we want this agent to behave is to select the actions that maximize its expected utility. So you're going to define a utility function, say this is the utility function I care about, and then you'll ask your agent, can you optimize this utility function for me? So there are characteristics of percept, environment, and action space that will dictate exactly how we're going to do this. And so there will not be one master algorithm that solves all this. We'll look at different types of problems and different ways of solving the different types of problems. This course will be about general AI techniques. So every technique that we'll cover will be one that is not specific to one specific problem, but that will be specific to a whole class of problems. And one of the things that we hope that you will learn is not only what the algorithms are like, but also understand for which real-world problems a certain algorithm might be the right fit. So how do you transform a real-world problem into a problem that can be put into a computer and solved by one of the algorithms that we covered? A motivating example throughout our lectures and projects will be the Pac-Man environment. Why? Because that's just a nice example that illustrates what decision-making agents need to do. So what is this game? This is an old computer game, and typically you are playing Pac-Man, the yellow little guy there, and that Pac-Man is supposed to eat food pellets, the white dots. It increases its score whenever it eats a food pellet. The ghosts are adversarial and try to chase down Pac-Man and essentially like reset it, make it die. The big white pellets are ones, if you eat those, you become a super powerful Pac-Man, so to say the ghosts now become edible to you. You can start eating ghosts temporarily and get even more points for that. So that's the nature of the game. As we progress, you'll see that a lot of the ideas we cover can be really nicely illustrated around this environment. That doesn't mean this class is about solving Pac-Man. It's just an illustrative example to understand in pictures how these algorithms work and so forth. So let's look at an example of the kind of agent that we might get out here. So here is an agent that you will know how to build by the end of lecture 7. So the AI agent is driving Pac-Man here. It's power pellet, so now it can actually eat the ghosts, which gives it a very big bonus. All right, it's going to be your agent 3 weeks from now. So what are the course topics overall? There will be 2 parts to the course. The first part will be largely on making decisions. Remember, about a half an hour ago, I said we could be inspired by the brain by thinking about what are the categories of decisions the brain makes. There are categories of decisions based on memory, or categories of decisions based on reasoning about what might happen, right? So the first part, we'll do a lot of the work on reasoning about what might happen. So simulation, and using simulation to decide what the right actions are. What will that be? Fast search, planning, solving constraint satisfaction problems. There could be adversaries. There could be uncertainty. Second half, things will get a lot more mathematical. We're going to use a lot more uncertainty, which we know is important to deal with real-world-like scenarios. There'll be a lot of probability there. Take the self-diagnostic for that. And the concepts we'll cover are Bayes nets, decision theory, and machine learning. Throughout the entire course, as we see different techniques, we'll tie them to applications. Then in addition, the last 2 or 3 lectures will be 100% dedicated to applications of everything we've covered at that time to real-world domains. Thank you. That's it for today.